Here you are starting to put together the pieces that will solve the problem. Again, this is not a linear process. You're not solving anything yet. You're collecting information, experimenting, seeing where the pieces fit. One of the most important things you do in this stage is to create other representations of the problem. I brought the visual representation over from the previous one, but I also want to create a schematic representation and maybe some graphical representations. Here I have a schematic representation of the system. I've created a coordinate system with the origin at the location where the raptor started. I have positive x going to the right. Here's the position along the x-axis that the professor starts, which happens to be 400 meters away from the raptor, so it's at an x equals 400 meters. I've represented my objects with points. I'm invoking the particle approximation for my system. When the raptor catches the professor, what that means is they are both at the same point in space, which I'm calling x. I've identified these concepts with notation: x sub r for the initial position of the raptor, x sub p for the initial position of the professor, and then x for the position where the raptor catches the professor. Note I also have an x here, which is the independent variable for the x-axis. Remember, when you use notation, never read your notation. Always read what the notation means. I would not read this as x sub r, xp, or x. I write it that way, but I read initial position of the raptor, initial position of the professor, and the final position of both. That's a schematic representation. What would a graphical representation look like? Well, I know I have positions and velocities, so I just did a little sketch. If I look at velocity as a function of time, I have two velocities, the velocity of professor, the velocity of the raptor. The velocity of the raptor is larger by quite a bit. They're constant for the entire time until some final time t sub f, which is one of the things I'm looking for, at which point I assume they both stop. If I want to look at a graphical representation of the position as a function of time, that would look like this in the lower graph. I would have two lines increasing x because they're both going in the positive x direction. Their slope would be constant because the velocity is constant. The raptor would have a steeper slope, and it starts at the origin, while the physics professor starts with a head start of 400 meters, but they end up at the same position in space at the final time. So now I'm ready to put notation on the things I'm looking for. I've already defined the location at which they meet. That's one of the things I'm looking for as x. And then there's also some final time when this happens, t sub f. Since I called the location just x, I'm going to call the final time just t, but I'm not reading it as t. When I see those, I'm going to know they mean the final location and the final time. Let's talk about other things you can do to brainstorm. Make sure you articulate any approximations, simplifications, and models that you are using. For example, we're doing the particle approximation. Copy down what you know and want to know with meaningful labels. So we did that already, making sure that you always read what those labels mean and not just the labels themselves, so you don't confuse things with similar labels. Identify relationships between quantities logically deduced. For example, if you have an ideal rope and the rope is connecting two objects 5 meters in length, there will always be a separation of 5 meters along the length of that rope between those two objects. For example, we deduced logically from the context of the problem that when the raptor catches the person in the particle model, that means they are at the same position in space. Those sorts of concepts for which there are no equations that you have to deduce logically from the context of the problem is something you do all the time in physics problems, and why it's so important to have a high-quality visualization stage, because that will help you do that process. Next part of the brainstorm is identify what physics applies to this problem. And then once you've identified physics that applies, what sort of relationships does that give you between the knowns and unknowns? Once you do that, start playing with your pieces. How do they fit together? Create equations from your relationships and your physical laws and principles. Once you have the same number of equations as unknowns, assuming the unknowns are in the equations, and the equations are linearly independent, you can solve for your unknowns. In this problem, what sort of physics applies? Well, both objects are moving with constant velocity, so I'm going to apply the uniform motion physics to this problem. What uniform motion physics tells me is that for 2 points, x initial and x final, I can find a relationship between them given by this equation. Well, how does that help me? Well, first of all, I have to identify my 2 points in time. And that's pretty easy. If time is equal to 0, I'm going to say the initial time is when the two objects started their run, and then the final time is when they connect. So my initial time, t sub I, I'm setting equal to 0. My final time I've already said is just t, and that means the time interval between them is just t minus 0, or that's t as well. Well, let's apply uniform motion physics first to the raptor. So there's some initial position for the raptor, which I have identified as x sub I sub r, initial and raptor, and that's just equal to 0. The final position for the raptor is where they meet up, which I've already identified as just x. And the velocity of the raptor is 25 meters per second. I've identified that everything is already in SI units, so my units are consistent. If I apply this physics to the raptor, then I get a relationship between these parameters, which is x is equal to the velocity of the raptor times time. That's great. I know velocity of the raptor, but I don't know x or t yet, so I can't solve. So let's apply uniform motion physics to the professor. I have initial position, which is x sub p, or 400. Final position is x, which is the same for the professor as for the raptor. I've identified that already. And the velocity of the professor is 7 meters per second. That gives me a relationship between those parameters given by this equation. And now I have two independent equations that both have my two unknowns, x and t, so that tells me I'm ready to solve the problem.